Yeah, the topic for this video lecture is work done, which is part of chapter on work, energy and power. We start with the definition of work done. Let's look at the definition carefully. Work done on an object by a force acting on an object when the object undergoes displacement is equal to dot product of force and displacement, F vector dot S vector. So if you look at the definition carefully, work has to be done on an object by a force which also must be acting on the object, and there has to be a displacement. So when you look at this quantity here, this is scalar product of two vectors, and result is a scalar quantity. So work done is a scalar, and unit is in joules. So Newton meter is actually joules. There's an alternate form. Work done can also be written in terms of magnitude of force into magnitude of displacement into cos of angle between force and displacement. We have to be careful about angle between force and displacement. Both vectors must be placed tail to tail. And some ways this is easier to understand. This quantity F is always positive, S is also always positive, for both being magnitude, whereas this term cos theta could be positive, 0 or negative. Hence the work done could be positive, 0 or negative depending on the angle between two vectors, force and displacement. Now suppose this is how the force and displacements are. So if you look at this angle here is acute angle. In that case cos theta will be positive, hence work done will be positive. In this case, what will work done? To find out work done, first we look at angle. Both are placed tail to tail. Angle between force and displacement is 90 degree. For 90 degree cos theta is 0. Hence work done also will be equal to 0. It doesn't matter what the magnitude of force and displacement are. If they are mutually perpendicular, work done is 0. In this case, what is the angle between force and displacement? Acute or obtuse? Look carefully. Actually the angle is obtuse angle, because to find angle first we must place them tail to tail. So this force vector should be placed like this, tail to tail. And in that case you find the angle is obtuse angle. If angle is obtuse, value of cos theta is negative, hence work done is negative. So basically we can say the sign of work done is dependent on angle theta, acute angle positive, obtuse angle negative, 90 degree 0. So calculation of work done is fairly simple. All we need to do, if mentally or actually on the sheet of paper, if we can represent both force and displacement in form of arrows, place them tail to tail, find the angle between them, work done is calculated. So we need magnitude of both and angle can be found using by placing them tail to tail or drawing a vector diagram. So it's a simple thing. Let's apply it in few cases. Here two blocks on a smooth surface are displaced by external force. So this external force is acting. The moment this external force is acting, it will lead to acceleration and hence the displacement. So here displacement is S. Find work done by normal reaction on each of the two blocks. We have to find where the work done by which force. So every time we have to be careful. Work done by normal reaction. How many normal reaction? Normal reaction will act at the contact between block M and 2M. So normal reaction is the contact force between two blocks, and there will be a pair of them. So there will be two contact forces. We need to find work done by each of the two contact forces, and both contact force will act on different blocks. Hence they will do work on block M and 2M. That's what we need to find. So what we need to do, first we need to find the magnitude, direction of displacement, angle, and we can find work done. Let's quickly go through this. First we start with what is the normal contact force, which can easily be found using basic principles of laws of motion. And we can find the magnitude of contact force will be equal to 2F by 3. and it will form an equal and opposite pair. So this is how the contact force will act on block M towards left and block 2M towards right, equal and opposite pair. So displacement vector, so let's calculate work done on which one first? Let's calculate work done by normal force on block M. So in that case, we'll take this force and displacement of M. So this is the displacement and this is the direction in which the force acts. They are in the opposite direction. Angle theta between them is 180 degree. So work done will be equal to magnitude of force into magnitude of displacement into cos of angle cos 180, which is minus. Hence work done will be equal to minus 2Fs by 3. So work done on M is negative. How about work done by contact force on 2M block? We mark both the direction of displacement vector and force vector. Both are in the same direction. Angle theta is 0. Hence work done will be equal to this magnitude into cos of 0, which is 2Fs by 3. So work done by contact force on 2M block is positive. Work done by contact force on block M is negative. So is it necessary that force doing work must be the one causing the motion? Actually not. This force is not the one which is causing motion. So it doesn't matter. It is not necessary that when we calculate the work done by any force, that force should be causing the motion. Even if it is not, still the work done can be calculated. Now let's take other one in vector form. Here block A, mass is given. It is placed on a rough surface, coefficient of friction is given, and this is external force. It is given in form of external forces 40 I cap minus 30 J cap, and direction of I cap and J cap are normal convention. Rightwards I cap, upwards plus J cap. So minus J cap indicates in the downward direction, and displacement is 5 I cap. So what is work done by external force on block A? So here there are two ways to calculate work done. One is in terms of dot product, or other one in terms of magnitudes multiplied by cos of angle. So here, since quantities are given in vector form, we will take the dot product, which is easier to find. So dot product method, dot product of force dot displacement, so 40 into 5 and minus 30 into 0. So basically the work done is 200 J. So what we notice here, the displacement is along the I direction, hence the component of force which is perpendicular to displacement, that component will not do any work. What will be work done by gravitational force here? This is the displacement. Which direction the gravitational force acts? Gravitational force acts in the downward direction. So what would be the angle between gravitational force and displacement? Angle is 90 degree. Hence the work done by gravitational force will be equal to 0. What will work done by friction on block A? So we need to find two things: direction of friction force and magnitude of friction force. Direction is pretty easy. Since the block moves towards right, friction force acting would be kinetic friction opposite to direction of relative motion, which is towards left. So friction force acting on block A will be towards left. And to find magnitude of friction force, first we need to find out normal reaction. So basically we draw the free body diagram of A. So these two components we express in I component and J component. So quite easily we can calculate the normal reaction will be equal to weight 100 plus 30, 130 Newton, and this is the direction. N is 130, so friction force will be equal to into 0.3, so 39 Newton. So angle between force and displacement is 180 degree. So work done, magnitude of force, magnitude of displacement into cos of 180, it will come equal to minus 195 joules. That is work done by friction force. So this way we can find out friction work done by each force acting on the particle. Or sometimes we can also we need to find out the work done by the resultant. Method is the same. What is the work done by friction on the lower surface which is at rest? So all forces act in pair. So if the friction force is acting towards left on block A, on the surface is pair force will act towards right. Okay, but to work done on lower surface will be dot product of force and displacement. Since the lower surface is at rest, it does not undergo displacement. Work done will be 0. So this is what happens in all the cases when we bring a moving object to stop on earth or ground. So like car, we apply brake, it comes to stop. But is there any work done by friction on the road surface? No. Work done by friction on the road surface is 0 because road is not in motion. So any surface which remains at rest, work done will be 0. Another question, a block is pulled up the rough inclined plane. So this plane, angle of inclination is theta, coefficient of friction is given as mu. Block of mass m is being pulled up the slope by a force F. Displacement is along the slope equal to S. Find the work done by external force. This should be pretty easy. Angle between them is 0. Hence work done is equal to F into S. Find the work done by gravitational force. So we'll use the second method, F into S into cos theta. So magnitude of gravitational force is mg downwards, and angle between two vectors placed tail to tail. Are they placed tail to tail? Yes, they are placed tail to tail. This angle is theta and this angle is 90. So angle between force and displacement is 90 plus theta. Hence work done will be force into magnitude of force into magnitude of displacement into cos of angle between two vectors tail to tail, 90 plus theta. Hence cos 90 plus theta is minus sin theta. Hence work done will be equal to minus mg into s into sin theta. What is this s sin theta? This is s, this is theta. S sin theta is the opposite side, which is h. So another way to understand would be s sin theta is the vertical component of displacement, which is h. So work done by gravitational force is equal to minus mg h. What will be work done by friction? Again, method remains same. Magnitude of force into magnitude of displacement into cos of angle between them. So what is magnitude and direction of friction force? Kinetic friction, opposite to direction of motion. Hence friction force will act downwards, opposite to displacement. Angle is 180. What is magnitude of friction force? Magnitude of friction force is equal to mu mg cos theta. We substitute these values. Work done will be equal to minus f into s. Negative sign because cos theta being minus 1. We substitute this value. This is the work done by friction. So in this case, block M is placed on inclined plane inside an elevator. So this is the elevator, this inclined plane, and block is placed here on the inclined plane. Elevator moves up by S. It has vertical displacement of S upward direction at constant speed. And block M does not slide on the inclined plane. So what does this word does not slide on the inclined plane mean? So its position with respect to inclined plane is not changing. It means whatever displacement inclined plane has, same displacement M also has. So if inclined plane has a vertically upward displacement of S, block M also will have a vertically upward displacement of S. So we need to find work done on block M by different forces acting on the block. So we will find work done by each of the forces acting on the block. What are forces acting on the block? Gravity, normal reaction, and friction force. And we finally will also find net work done by all forces. So finding work done is pretty simple. We need to find the magnitude and direction. If we represent each force in terms of arrow or vector form, we can find out work done quite easily. So one by one, let's start with gravitational force. This is the displacement direction. This mg is acting downwards, hence angle cos theta is cos 180. So work done will be equal to force, magnitude of force into magnitude of displacement s into cos of angle between them. Hence it will be equal to minus mgs. That's the work done by gravitational force. Next one, we look at normal reaction. Normal reaction we know is equal to mg cos theta. There is no acceleration. So this mentioned, it is moving the constant speed. Hence acceleration is 0. So in case of 0 acceleration, normal reaction is equal to mg cos theta. What is the angle between normal reaction and displacement? Let's represent this is the normal reaction, but this is not the angle between normal reaction and the displacement. To find the angle, we need to place them tail to tail. We need to place normal reaction like this. When we place not like this, we find the angle between normal reaction and displacement is theta. So this term here cos theta. What we work done? Magnitude into cos theta. So this will become equal to mg into s into cos square theta. That's work done by normal reaction. Now we find work done by friction. So first we mark the direction of friction force. Friction force will be equal and opposite to mg sin theta. It is the case of static friction because no slipping is taking place. So this is magnitude mg sin theta. This is the direction. And what will the angle? With normal angle was theta. So with friction force which is perpendicular to it, angle will be 90 minus theta. And this term will be cos 90 minus theta. What is work done? This term into displacement into this term. And this term is sin theta. So mg sin theta into s into sin theta is equal to mgs into sin square theta. So what is the resultant work done? We'll add up work done by each force. So net work done, we add up these two. Summation of work done by normal reaction and friction force is equal to plus mgs. Work done by gravity is minus mgs. We add it up. Net work done by all forces acting on mass m is 0. So is it by chance or is there any logical explanation why the work done has become 0? Yes, there is a logical explanation. Since mass m is not getting accelerated, the net force must be equal to 0. Since the net force is 0, the work done by net force also must be equal to 0. So this is a typical Atwood machine. One side mass m, other side 2m. Find work done by string force on two blocks in first t seconds after the system is released from rest. So we have to find work done by string force on two blocks. There will be string force acting on block m, there is string force acting on 2m. We need to find work done in first t seconds after the system is released from rest. So first we need to find the displacement also. What is the displacement in first t seconds? And to find displacement we need acceleration. Both will have equal and opposite acceleration. And acceleration can easily be calculated, which comes equal to g by 3 in the opposite direction. So this will have upward acceleration, this will have a downward acceleration. So in time t, this moves up by distance d, and this has equal magnitude of acceleration. Hence the magnitude of displacement also will be same, downward d. And this is the direction in which the force acts. So tension or string force on m is in the upward direction, and string force on 2m also is in the upward direction. So what is magnitude of displacement? Using 1 by 2 at square, we substitute the value of acceleration g by 3. Displacement d is magnitude is equal to gt square by 6. Now to find work done, one more thing we need to find is the value of tension force. How do you find t? This block acceleration is known. Acceleration is a upwards. If acceleration is a upwards, the tension force will be equal to m into g plus a. M into g plus a. So using t is equal to mg plus a, we find the value of tension force will be equal to 4 mg by 3. A being g by 3. We could also find out using this block. In this case, acceleration is downwards. In that case, what we need to do, mass of these two blocks, 2m into g minus a. Both will come same. So we have everything what we need to calculate work done now. We have magnitude, direction of force as well as displacement. So on work done on block M, both T and D are in the same direction. Hence work done is simply the product of two, T into D. On 2M, they are in the opposite direction, and work done will be equal to minus T into D. So what is the net work done by string on two blocks? Will come to 0. That's what we also use in case of constrained motion. Work done, net work done by string on the blocks connected at its two ends will be equal to 0. It will do equal and opposite work. So far what we had dealt with was work done by constant force. What happens in case of force is not constant? Work done by variable force. And we are taking, so force can vary with time and force can vary with position. We are talking about force which is varying with position. The magnitude and or direction of force changes with position. So when force changes with position, if the displacement is taken to be infinitely small, then for infinitely small displacement, the force can be treated as constant, and hence for infinitely small displacement, we can use our normal definition of work done. Work done will be equal to dW, work done also will be small, magnitude will be small, will be equal to F dot ds, ds is the displacement. And in vector form, if the displacement can have component in all three directions, dx is the displacement component in x direction, similarly y direction and z direction. So displacement ds or dr can be written as dx into I cap, dy j cap plus dz k cap. So similarly, force also can have components in x direction, y direction, z direction. So this is the work done by a variable force when the displacement is from A to B. This is general expression. Now, if the motion is only in one direction, let's assume the motion is only in x direction. In that case, dy and dz will be 0. Y coordinate and z coordinate will not change. If these two terms are 0, only part which will be relevant will be, so y component of force and z component will not do any work. So work done in that case will be equal to only fx into dx. So this is the work done in case of one dimensional motion. And in change of position also, what will change only will be the x coordinate. Initial position x coordinate xi, final coordinate xf. That's work done when it is displaced from initial position xi to xf in one dimension, fx into dx. And when we look at this expression is very similar to y dx. What is integration of y dx? Area under yx curve. So if in place of y, what is here? In place of y, what we have plotted? Force is plotted on y-axis. So this curve gives the variation of force with position. So what we notice here, as the x coordinate is increasing, the force also is increasing in a non-linear fashion. If force was increasing in the linear fashion, this would have been a straight line. Curve means it is varying in a non-linear fashion. So this term, work done between xi and xf, will be equal to area under the force displacement curve between xi and xf. So there are two ways of calculating work done by a variable force. In case of one dimensional motion, it can also be calculated if we plot force versus displacement. We can calculate work done as area under the curve between initial point and final point. This is possible only in case of one dimension. So suppose displacement is taking in all three directions, we need three such graphs: displacement in x direction, x and fx, y and fy, and z and fz. Then we can calculate force work done in due to component of force in x direction, y direction and z direction. So let's take up a question on variable force. Force is given as xy I cap minus y j cap. Let's see what we understand from this expression. Force has I component as well as j component. It doesn't have any k component. And I component depends both on x coordinate as well as y coordinate, whereas y component depends only on y coordinate. So if x coordinate, if we, okay, this expression. Now, what is work done when object is displaced from O to A? So it is moved from O to A. What is the work done? Can we calculate work done? So think in your mind what would be our method to calculate. First thing what we need to think, is it one dimensional motion or multi-dimensional motion? O to A is a straight line or one dimensional motion along x-axis or I cap direction. Which component will do work? Only the I component will do work. J component is irrelevant. That's the first thing. Displacement is along x-axis. Only x component of force Fx will do work along path OA. Now we have to, once we figured out, now we have to find out what is the force along, what is Fx. As we move along O to A, the x coordinate is changing from 0 to A. But is the y coordinate changing? No. Y coordinate all through the path is 0. Hence y value is throughout 0. It means as we move from O to A, Fx is all through equal to 0. Hence work done also will be equal to 0. What is work done when displacement is from A to B? How would you calculate work done from A to B? Let's think of method. What kind of motion it is? It is 1D motion. But this time it is along y direction. Hence, and it's a variable force. So it will be equal to Fy into dy. That would be the work done, and since force is variable, it will be integration of Fy into dy, lower limit y equal to 0, upper limit y is equal to A. So displacement along y axis, hence only y component of force will do work, and that will be equal to Fy into dy. We substitute the values, we find work done will be equal to minus A square by 2, which makes sense because force is acting in the downward direction, displacement is taking place in the upward direction. So what happens if the displacement is from O to B? If the displacement takes place from O to B, how do we find out work done? Now in that case, displacement has both x component as well as y component. Hence work done will be equal to Fx into dx plus Fy into dy. And when you substitute the value of Fx, this becomes equal to 0 to A xy dx plus minus y into dy. Minus y is your y component of force. You have to keep the sign also in account. Limits 0 to A, 0 to A. X coordinate is changing from 0 to A, y coordinate also changing from 0 to A. First integral. Is it possible to integrate this term here? This term dx, I can integrate x into dx. But can we integrate y dx? Y dx is not possible because we can only have either a constant term or only variable term possible is x. So what we need to do to integrate, we need to first get rid of y. How do we get rid of y? I have to express y in terms of x. So I must have a relationship between x and y, then only I can integrate. Then only I can substitute y in terms of x. Is there any relationship between x and y? So if we move from O to B, what is this path of trajectory? This path is x is equal to y. It's a straight line. So what is the equation? Y is equal to mx plus c, or it is of the form y is equal to mx, m is equal to 1. So this equation is x is equal to y. So since we are moving along this path, this is the relationship. So now I can substitute in place of y equal to x. So this expression becomes equal to x square into dx. Now I can integrate. So whenever we have such expression, it cannot be directly integrated unless we know the path, unless we know the relationship between x and y. So that's why I say this integral depends on the path we take. If you go straight line, it has some work done. If I take some other path, the work done will be different. It depends on path dependent. So if we substitute, now it is simple. So this would be integration of x square dx, which will be x cube by 3. Substitute the limits, it will become equal to a cube by 3. Similarly, this one will equal to y square by 2. So minus y square by 2, some limits, a square by 2. So work done depends on the path or trajectory, which is relationship between x and y. So there are some cases where it does not depend on path. There are some cases where it depends on the path. So let's come to next one. Force is given as 3i cap minus 4j cap. First, moment you look at the force, first you should think of, is it a constant force or a variable force? It has no variable term here. There is no x, y or t. It means the force is a constant. So in this case, find work done when the displacement is from O to A to B to C. So this is a path. It has 3 straight displacements. How do you find the work done? So one way of finding work done is I can calculate work done along each part of displacement. So that will be f dot r1 vector plus f into f dot r2 vector plus f dot r3 vector. Now since force is same or constant, I can take force as common. So force vector dot r1 plus r2 plus r3. And what is this? Is vector sum of 3 displacement. What is vector sum of 3 displacement? Is the resultant vector OC. Thus r1 plus r2 plus r3. So this is the my resultant vector. So what is work done? Work done is simply f dot resultant displacement. And this is possible only when the force is constant. So this is an important observation. Work done is independent of the path when the force is constant. And hopefully you have understood the reason also. Okay, when we calculate work done along small displacement, force can be taken out. It becomes vector sum of all small displacement, which is the resultant displacement. So for a constant force, work done depends on the resultant displacement only. It is independent of the path. So work done along OABC is same as work done along OC, or if we take the particle along any random path, as long as starting point is O, end point is C, displacement is same, work done will remain the same. Is independent of path. So what is work done here? Pretty simple to calculate. Displacement will be equal to 2i cap plus 2j cap. We take the dot product and the work done comes equal to minus 2a. So what will work done if the displacement is along circular path? So suppose we take this as the path. This is how we move the particle from O to C. In that case, what will be work done? The answer should not even take few seconds. The work done is still the same. Doesn't matter what the path is. It still will be equal to minus 2a. Path independent. Now we will take one more variety of force. Work done by force which is always tangential to circular path. So object is moved along the arc of a circle from A to B. Force is acting in such a way that is always tangential. If the force is constant, so what will be the work done by F? Is the force constant? First answer is no. Force is not constant. So work done, which method I have to use? I cannot use force dot resultant displacement. I have to use F dot ds for a small displacement and I need to integrate. Now when we have dot product between the two, I can write as magnitude of force into magnitude of displacement into cos of angle between them. Since the force is always tangential, cos theta is equal to 1. So it is equal to F ds. Now it is a 2 scalar quantity. Now F is constant, so F also can be taken out. It is integration of ds. What is integration of ds? ds is a scalar here. Integration is nothing but addition. What is addition of all small displacements? Scalar addition. Scalar addition is, it is scalar sum of small displacement is nothing but path length. Length of the path it took from here to here. And what is the path length in this particular case? 1/4 of the perimeter of circle, which is pi r by 2. Hence work done will be equal to F into pi r by 2. So this important point, if the angle is 0 or constant, we can find out work done with this method. In this particular case, angle was 0. If angle was constant also, we could have used the same method to find out the work done. Integration of scalar quantity ds is equal to path length. That's important point you should remember. Now we take another force P, which is always horizontal. So this is a force P acting as the particle moves from A to B. What is work done by P, which is always horizontal? Any difference? Is the force P constant? See, the force is constant here. Ignore this word no here. So what will work done here? Work done, again, if we take small displacement, is P dot ds. Since P is a constant, it can be taken out of integration sign. It is P dot ds. You notice the difference between the two? This was scalar quantity magnitude of displacement. This is vector form of displacement. So it is vector sum of all displacement. What is this term? This was the scalar sum of all small displacement. This is vector sum of all displacement. The vector sum of all displacement is a resultant vector also. Is equal to, so what is vector sum of all small displacement along this path? It will be vector A to B. So what is that vector? Resultant of this will be Ri cap plus Rj cap. And when you take the dot product, P can be written as Pi cap. Hence work done will be equal to P into R. So this is very important. You understand the difference between the two. And you should also note what is the integration of scalar ds. What is the integration of vector ds? This is scalar sum of small displacement. This is vector sum of small displacements. Here, what is work done by gravitational force to move an object of mass m from O to P? So this is a random path starting from origin. It is moved to a point P having coordinate A and H. Mass is m. What is the work done by gravitational force? Any such question, first thing we should think of is the force constant or variable. Gravitational force is a constant. Hence, work done is independent of path. We will not worry about the path it is taken. We will only worry about resultant displacement. And resultant displacement is final position vector minus initial position vector. Initial position vector is null vector. So it will be equal to Ai cap plus Hj cap. That's my displacement. So work done will be equal to dot product of force vector and displacement vector. We substitute those values. We find work done is equal to minus mg into h. There is no a term here. So it is independent of displacement in the horizontal direction. Work done is independent of A, or work done is same if from O we move to any point which lies on the horizontal plane passing through P. So if we draw a horizontal plane passing through P, all points, the y coordinate will remain the same. Hence work done to move an object from O to any point here on this line along any path will be again minus mgh. So work done is same if displacement from O to any point on horizontal plane passing through P. Because it only depends on y coordinate change, or it only depends on component of displacement along y direction. The force is acting along y direction here. Now we come to work done by spring force. We know the spring force is equal to minus kx. K is called the spring constant and x is displacement from the mean position. So this is the unelongated length and this is taken as origin. So if spring is, suppose we stretch the spring by distance x, then the spring force will be equal to, so from here it has been stretched by distance x. Which direction the spring force will act? The spring force will act in the direction towards the mean position, or it will act in a direction opposite to displacement. Hence the negative sign. The negative sign indicates opposite direction. This is one dimensional motion. Plus minus sign is adequate to indicate the direction or vector. So what will work done to change the position of spring end from xi to xf? It is one dimensional motion, variable force. So my formula for calculation of work done will be equal to integration of fx dx, or I can write as f into dx into cos theta, magnitude of force into displacement into cos of angle between them. So magnitude of force is kx, displacement is dx, angle between them is 180 degree. They are in the opposite direction, hence the -1. So this, and I need to integrate from where to where? From initial position to final position. If I integrate quite easily, I can find the work done to be equal to -1/2 k into xf square minus xi square. If we take a simpler case, when the initial position is at the origin and final displacement is x, in that case work done will be equal to, so work done will equal to -1/2 kx square. What will happen if the final position is not x, minus x? Final position minus x indicates compression of x. Will the work done be any different? In place of x, we will substitute minus x. Since the term is x squared, the work done is same for compression of elongation of x. It only depends on magnitude of displacement, not on the direction. We can also find out work done using graphical method. So spring force Fx is equal to minus kx. It is possible to plot a graph between Fx and force and displacement. Equation is in form of y is equal to minus Fx. So this is the graph between force and displacement. So slope is equal to minus k. So what will work done if displacement is from xi equal to 0 to x, final position x? It will be area under the graph from x equal to 0 to x. So this is x0, this is x. Area under the curve, this is the area under the curve. Can we calculate this area? Quite easily. Area under the curve will be equal to, and the force will be equal to minus kx. So area of this triangle is equal to -1/2 into x into kx. So -1/2 kx square. What happens if the displacement is twice as much? It is from 0 to 2x. Again elongation. So here this will be the shape from 0 to 2x. So force also will become equal to -2 kx. So what will be the work done? Work done will equal to -1/2. So area will be 1/2 into this term, which will be equal to -1/2. So this minus should not be there. So minus, if only one of these two minus, 1/2 into -2 kx into 2x. It is equal to -2 kx square, which is 4 times of this. So when displacement is twice, work done is 4 times. So this brings us to the end of